Welcome to my video course on Railway Safety and Systems Engineering. When most of us think about railways, we immediately picture the obvious physical stuff, right? The heavy steel tracks, the overhead wires, and massive metal trains rolling from station to station. But to truly grasp how a modern railway operates, and more importantly, how it actually stays safe, we need to completely flip our perspective. We have to stop looking at it as just a random collection of machines and infrastructure. Instead, we need to start viewing it as a complex, living ecosystem. Because just like in nature, no single part of this environment exists in a vacuum. Literally everything is connected, and everything relies entirely on the health of the whole. Here's a quick look at our agenda for this explainer. First, the railway ecosystem. Second, core railway subsystems. Third, complex system interactions. Fourth, managing subsystem interfaces. And finally, number 5, emergent properties and safety. Let's just dive right in. Section 1, the railway ecosystem. Okay, so the absolute first thing we need to do is define exactly what we mean when we throw around the word system. Simply put, a system is a set of elements, subsystems, or assemblies brought together to achieve a specific purpose, like, say, moving thousands of commuters safely across a busy city. But the real kicker here is the second half of that definition. A system possesses qualities that are not present in the individual elements themselves. In engineering, we call these emergent properties. And honestly, this perfectly captures the entire concept of safety. Because safety isn't just a component you can grab off a warehouse shelf. You can't just point to a shiny piece of metal or a line of computer code and say, yep, there's the safety. No way. Safety is the ultimate emergent property. It's the final result of all these totally different elements perfectly integrating and working in harmony. Section 2, core railway subsystems. To really understand this ecosystem, we have to get to know the different species living inside it. We've got the permanent way, which is your tracks, ballast, bridges, and tunnels. Then there's electric traction and power to provide the juice. We have the rolling stock, which are the trains themselves. We've got signaling to control movement, telecommunications to transmit vital data, and finally, operations and drivers, the human element. You really have to treat these like distinct species in a biological habitat. They all have completely different characteristics and functions, but they absolutely must coexist, communicate, and support one another for the whole ecosystem to actually survive. Moving on to Section 3, complex system interactions. So in any complex system, a minor change in one subsystem sends a ripple through the entire environment. These connection points are basically the synapses of our railway ecosystem. Let's look at a practical example, the interaction between rolling stock and signaling. Now, you might think placing a signal is just about checking a map and finding a good spot, but it's actually entirely dependent on the physical braking characteristics of the train. The distance between a caution signal and a danger signal has to perfectly account for the time it takes a specific massive train traveling at a specific speed to safely brake to a halt, plus a healthy safety margin. So think about what happens if you introduce a brand new, heavier fleet of trains into the mix. Their braking distance might be longer. That single, isolated change means your entire existing signaling subsystem might suddenly be dangerously inadequate. Here's another super practical physical interface challenge, a track junction. Train geometry, specifically the overhang from the wheels to the actual nose of the train, dictates exactly where track clearance points have to go. So the permanent way engineers, they lay down the physical track. But the signaling engineers, they need to know precisely where a train's wheels will be relative to its nose so they can safely place axle counters or track circuits. If they don't account for that vehicle overhang, the signaling system might actually think a junction is clear, when in reality, the nose of a train is still sticking out and fouling the adjacent line. It's just a perfect example of two totally different subsystems requiring exact dynamic coordination. Historically, railways were built using what's known as a discrete discipline approach. The track engineers did their job over here, the train builders did theirs over there, and they just met in the middle using very rigid, static standards. And for a long time, as long as everyone stayed in their lane, it worked. But today, that approach is completely dead. We now have to rely on systems engineering. Modern frameworks have to constantly manage dynamic, complex, and concurrent interfaces. And the reason why is simple: modern technology. Take radio-based train control, for example. Signaling is no longer just colored metal lights on the side of a track. It's digital data beaming invisibly through the air, directly into a cab's onboard computer to automatically calculate braking curves. The boundaries between these different engineering disciplines haven't just blurred, they have completely dissolved. Section 4. Managing Subsystem Interfaces. If we keep viewing the railway like a human body, then the telecoms network is undeniably the nervous system. Its roles literally span across everything. It handles operational voice, which ensures secure, clear communication between drivers and signalers. It carries signaling data, acting as this invisible bearer service for all those modern train control systems we just talked about. And of course, it manages passenger information, keeping the stations updated in real time. The telecoms network touches every single subsystem. It is the vital data highway that prevents a total system-wide breakdown. To actually manage all these crazy complex interfaces, engineers have a pretty strict playbook. First, they identify the system goals. Second, they define all the technical and human interfaces. Third, they assess the impact of degraded modes. And fourth, they verify the holistic integration. Let's pause on step 3 for a second. We have to ask ourselves a really critical question. What actually happens when a telecom network fails? Suddenly, the automatic routing drops out. The signals might automatically revert to a fail-safe danger state. And at that exact moment, the technical system steps back, and the humans, the signalers and the drivers, have to rapidly intervene. The whole interface management process has to anticipate this exact kind of scenario. You have to ensure that when the technology inevitably degrades, the human rules and training are robust enough to catch the falling pieces safely. Section 5. Emergent Properties and Safety. I really want to hammer home this central thesis of systems engineering. The safety behavior of a system cannot be determined by the safety behavior of its individual components alone. Listen, you can go out and buy the most mathematically perfect, highly reliable, solid-state interlocking computer on the planet, but it is entirely useless and honestly potentially dangerous if the telecom bearer drops its data packets, or if the user interface on the signaler's desk is confusingly designed, or if a track circuit simply fails to detect a contaminated railhead. True safety only emerges when every single one of those pieces shakes hands flawlessly. And we find that true system resilience is really put to the test during degraded conditions. When things break down, say a massive power failure hits a whole sector of the track, the highly interdependent nature of the modern railway suddenly becomes a massive vulnerability if it wasn't engineered correctly from the start. During these degraded mode operations, we see a huge increase in reliance on human interaction and special verbal operating rules. The safety risk shifts incredibly fast. It moves away from automated technical fail-safes and lands squarely on the shoulders of the human operators. So, understanding how the system behaves when it's broken is just as important, if not more so, than understanding how it behaves when it's working perfectly. So, this leaves us with a pretty provocative final thought regarding the future of system resilience. As we push further and further into next-generation automation, where computers are handling way more of the driving, the routing, and the interface management, how exactly will these fragile interfaces change? Is eliminating the human element going to make the ecosystem more robust? Or will it just create new, unforeseen, emergent vulnerabilities when things inevitably break down? It's really the defining question for the next era of systems engineering. Thanks, we can see you in the next video.